So here's the title of my presentation, dreamed up by a graduate student whose hard work is matched by his enthusiasm for the subject matter. Here are our collaborators, Berkeley, Lawrence Livermore Lab, ITRI in Taiwan, and Cal Poly San Luis Obispo. I want you to take away two words from today's presentation, and the first of these is zinc. And I'll explain as I go through here. So, I'm losing my microphone here. I'll simply hold it. We need energy storage quite clearly for the devices we've been talking about, but also for cell phones, laptops, and so on. More pressing, actually, is the need for extensive development of energy storage if we're going to use renewable energy, which I think is essential to deal with some of the problems that Paul identified. Batteries and supercapacitors are obvious ways of storing energy. And I'm going to be talking mostly about batteries, a little about supercapacitors, and I'm mostly going to be talking about a zinc battery. Now, zinc is cheap, non-toxic, and abundant. But hitherto, zinc batteries have not been rechargeable. So if you go down to your corner drugstore and buy an alkaline battery, you are buying a zinc battery, but you cannot recharge it. If you try to do so, you find that you can't stick any energy back into it. So that's a major issue with zinc batteries, which fortunately we've been resolving over the past few years here at Berkeley. We've been discovering that if we use a special electrolyte, an ionic liquid electrolyte, we can in fact recharge these batteries. And I'll demonstrate that to you in a few moments. So here's an outline of my talk. I want to talk briefly about some background on manufacturing these batteries and superconductors by printing. Some recent basic work on zinc deposition. Zinc deposition is what happens in a zinc battery when you charge it. I want to talk about integration with the thermoelectric generator, which Paul's already touched upon. And then I want to step aside from the ruling paradigm of this meeting by talking about large-scale energy storage. So I'm going to go big instead of small. And then I'm going to talk about some first successes in large-scale printing. So the second word I want you to take away from this meeting is printing. And I'm talking about printing either at a small scale here. This is a laboratory scale printer, which we call a dispenser printer, which is capable of printing something like a postage stamp size device. So it's very useful for the sorts of devices we've been talking about so far. But also I want you to draw your attention to this flexographic printer, which sits down here, which is at Cal Poly San Luis Obispo, and is capable of printing Time magazine. Each of these stations down here can print a different ink, a different color, for example, and we're collaborating with the folks at Cal Poly to work towards using this for printing large-scale batteries. So why are we interested in printing? Well, because electrochemical reactions such as existing batteries are heterogeneous reactions. They occur at an interface between an ionic and electronic conductor. So you need surface. So the manufacturing of batteries, or for that matter supercapacitors, is the creation of large amounts of surface area per unit volume, centimeter cubed and meter cubed, or whatever your favorite volume unit is. So when you think about printing, it creates large amounts of surface area per centimeter cubed. Think about this morning's Chronicle. The ink on it is very thin. It has a fair amount of surface area. If you went around and measured it, it's probably about 5% of the area of the pages. But because it's very thin, it has a very large surface area per centimeter cubed. So we can exploit that printing technology to create the surface area which we need for batteries or for supercapacitors. And that's what the drive of this research is about, and why the word printing is important. Now, I mentioned you can't recharge a conventional zinc cell, an alkaline cell from the corner drugstore. And the reason you can't do that, this slide is a little hard to see, but this is what you get when you deposit zinc from a water-based electrolyte, such as sits in your alkaline energizer cell. You get these nasty things called dendrites. So the zinc that comes down when you're trying to store energy in this thing forms these fern-like structures. Now, that's bad enough in itself because these structures tend to create internal shorts. But what's even worse is when you discharge this thing, when you now take the zinc back into solution, these things fall apart and all of a sudden the zinc that's in your cell is in the form of a sludge which is not electrically connected to the outside world. So cycling of cells with water-based electrolytes is impossible. What was discovered here, and also at other places as well, is that if we take one of these ionic liquids and create a gel polymer with it, we can replace the water-based electrolyte with this stuff, and lo and behold, we can cycle it, and I'll show you some of those results in a few moments. Big question, of course, is why? And over the past 6 to 9 months, we've discovered the answer to that question. It comes from some surface characterization techniques based on optical microscopy, electrochemical atomic force microscopy, and ultra-small angle X-ray scattering. I only have time to talk about the middle one of these, and I'm going to show you a sequence of slides for the deposition of zinc from one of these ionic liquid electrolytes onto what's initially a smooth platinum substrate. So this is a small patch on the surface of an electrode on which we're going to deposit zinc. Remember, a micron is a hundredth of the thickness of a human hair, so this is a very small dimension. And here we've got the vertical dimension on approximately the same scale as you and I will see it. So that's the initial substrate. Here's what it looks like after we deposit what corresponds to 200 monolayers of zinc. You can see that some roughness develops. But remember, this scale here, this will be smooth and shiny on the macroscopic scale of things. If we go to 400 monolayers, things look a little rougher, 800 monolayers, finally 1400 monolayers. This shows the typical hexagonal structure of zinc deposits. This may look to the untutored eye as a little bit on the rough side, but that's a great deal better than the dendritic deposits when we tried to use deposition from a water-based solution. So this is a decent amount of charge which has been deposited on this surface. This gives us a quarter of a milliampere hour per centimeter squared. So we're very pleased with that result, and the result that we could use now a rechargeable zinc battery, and we have some understanding of how it happens. Let me change now for a moment to supercapacitors. Over here on the left-hand side, I have a conventional capacitor with parallel plate electrodes and a dielectric we stick in the middle, and when you apply a potential difference across those plates, of course, the dielectric polarizes, so you can store a limited amount of energy that way. A supercapacitor works on essentially the same principles, except that it has a very large surface area. Remember, again, large surface area, typically formed by carbon electrodes, and that there are ions within the pores of these electrodes, there's an imbalance between negative charge and positive charge, and so we can store our energy in this thing here. So what can we do with supercapacitors? Well, this is a slide which summarizes where we were actually a few years ago when Christine Ho finished her PhD dissertation. She's been mentioned already. She's the chief technical officer of a company called Imprint Energy, which is exploiting printing for generating zinc cells. And you could see that this thing Christine was able to cycle these things up to about 70 cycles. They would probably have gone beyond that, but she got bored doing it. And achieved reasonable energy densities, about 130 watt-hours per kilogram. Lithium batteries, for example, are in the range of 152 to 200 watt-hours per kilogram. So that's all very decent. But what I've pulled, and those of you who've been to these talks before have probably seen this slide several times. What you probably haven't seen is what came out of some work she did in the very early days of her graduate study, which was on a supercapacitor. And lo and behold, she was able to cycle a supercapacitor 9,000 times before she got bored. So that was a substantial achievement, and the numbers up here for the electrochemical performance are also fairly attractive. So we have actually gone back now to starting to look at supercapacitors. And so we are printing supercapacitors. These are actually printed with our dispenser printer rather than a large-scale printer. But we print nickel collectors. Those are the plates on either side of this thing. We have activated carbon electrodes, and in the middle here we have a gel electrolyte. And This looks ugly, but bear with us. This is stuff we've done over the past couple of months. It will get neater as we go along. So here we have a printed supercapacitor. This is the current collector, 2 electrodes. You can't see the bottom one, with an electrolyte sandwiched in between. And these are some electrochemical performance data. I'll just pull your attention to one of these. This is the round-trip efficiency is not particularly high. It's only 20%. 20% of the energy you stick in comes out. But we think we know how to deal with that, how to improve things. And the rest of the figures are looking quite attractive. Paul's shown some of this slide already. Now let's think now about integrating some of these devices, supercapacitors, batteries, and a printed thermoelectric generator. So the idea here, Paul has emphasized this, is that the thermoelectric generator takes care of the sleep mode, similar to what Igor talked about, and then when we get to gathering data and transmitting data, then we call on the zinc battery and the supercapacitor to provide the extra oomph we need in order to conduct those tasks. And here's some targets for our prototype device of this nature. What you can do, if you can print this thing, is then roll it up into something that, for those of us who are over 50, is approximately the size of a film canister. And then you mount it so that this surface is hot and this surface is cold, and lo and behold, then it generates energy, makes measurements. These sensors here could be sensors of temperature, acceleration, radiant flux of some sort. All kinds of sensors ought to be able to work with this. Naturally, of course, we're not attempting to print these 2 devices. This is a Texas Instrument radio, which we would couple into this thing. Can we print a thermoelectric generator? Well, you bet you can. So here's how that works. So we mechanically alloy some semiconductors, mix them with epoxy, and print them. Here I'm showing the dispenser printer being used for this purpose, and printing bismuth telluride and antimony telluride as the 2 components in a thermoelectric generator. And this is what it looks like. So here's a flexible substrate on which we printed thermoelectric lines. So we're going to couple this to a battery and maybe eventually a supercapacitor as well. And here's what it looks like when the electrochemical performance, when this guy charges this guy, and then when this thing's charged up, we discharge it in some way which is to mimic what happens when you need high power for transmission or some other task. This device we're rather proud of. It's found its way onto the cover of a journal of micromechanics and microengineering, so we're very happy with that. Okay, let me switch gears now because I want to talk about larger scale energy storage. Paul indulges me when I talk about these things, even though it doesn't fit nicely into the subject of today's talk. I have what I think is a very impressive slide to show you, which is this one. Some of you may have seen it already. It comes from a friend and former colleague of mine who heads the Fraunhofer Institute on photovoltaics in Germany. It impresses me, first off, because there are only 23 hours in Germany, but that's a different matter. What's impressive is on this particular Sunday in spring, I think it was in 2012, all of Germany's power generation was from photovoltaics. No nuclear, no coal, just a trickle of water and some wind. Okay? But the message is quite clear. In Germany, at least some of the time, you don't need baseline power. You can run it all on photovoltaics. Now, that's the good news. The bad news, of course, is that for these hours of the day, you obviously can't use photovoltaics. So this drives home the urgent need for developments of energy storage. Presumably, this would include, and maybe even mostly be, printed batteries and supercapacitors. So this brings me to electrochemical energy storage on a larger scale. Capacitors are very good in terms of delivering power. Fuel cells very good in terms of delivering energy. And batteries and electrochemical capacitors are somewhere in between. But all these things would have to be big in order to satisfy this need in connection with photovoltaics. So in my last few slides, I want to show you some of the things we've been doing in collaboration with Cal Poly San Luis Obispo. So now think about think about this flexographic printer here, printing maybe on a stainless steel web or some other web, a cathode, it goes along then, an electrolyte gets printed, and an anode gets printed. So we've done that not using this machine, but using a smaller scale flexographic printing, together with the colleagues from San Luis Obispo who sit in the audience here. And this is the lower half of a graduate student, and these are electrodes that have been printed on the stainless steel strip by this flexographic printing. The electrodes are cathodes, and they are about 5 centimeters by 5 centimeters. So that's the first step. The next steps, of course, are to print the electrolyte and the other electrodes. The other electrode is no difficulty. We've done that already. Printing the electrolyte's a bit trickier, but I don't want to go into the details of that for the moment. We were successful in doing that because of some examination of the rheology of what we were doing. So here we have toothpaste being squeezed out of a tube. Think about the rheology of that. Toothpaste is shear thinning, which means if you apply a big shear to it, it acts like a liquid. If you apply a small shear to it, it acts like a solid. And you want that, of course, because when you squeeze the toothpaste tube, you want the toothpaste to come out, but you don't want it to drip off the end of your toothbrush when the shear stress goes down. So it turns out that inks, such as are used for printing the New York Times, which we call graphic inks, have that characteristic, that they are shear thinning, that you need to get up to a yield stress of around 100 pascals before they'll start to flow properly. And if you're below 100 pascals, then they'll stay where they're supposed to be. Our initial inks that we worked with were down around here someplace, and they printed terribly. So fortunately, the graduate student working on this project, a guy called Joe Wang, who now works for Applied Materials, found out that he could modify the composition of the ink that we use for printing this cathode to bring up the yield stress to these values, and then we were able to successfully print those cathodes. And there's a slide of a manganese dioxide that was printed. It was actually printed in 3 layers, and it looks fine. That's what it should look like. Over on the right, there's a print of a piece of the electrolyte. Remember, this is a gel polymer. This, I think, was made in the dispenser printer. How does it perform electrochemically? Well, those are stainless steel foil, flexigraphically printed manganese dioxide, dispenser printed gel electrolyte, and a zinc foil on the top. And this thing charges and discharges perfectly well. So we've cycled it up to over 100 cycles now before we got bored. And the printed cell is yielding about 50 to 100 milliamp hours per centimeter cubed, and a rechargeable AA battery, a lithium cell, for example, would show somewhere between 120 and 250 milliamp hours. So we're in the right ballpark, even at this point in time. So my conclusions, we have a better understanding now of why zinc batteries can be made rechargeable. We are revisiting printed supercapacitors. We printed TEGs and integrated them with a printed battery. And we're now collaborating with Cal Poly San Luis Obispo on flexographic printing of cathodes as a first step in printing grid-scale batteries. So thank you for your attention. Everybody's hungry. Oh, there's one over there. I'm sorry.
So how might this technology be applicable to things like EV batteries? Are there weight considerations that would make it unsuitable?
I don't think so. Zinc is more dense than lithium, that's true. But when you add all the other battery components in, that's not a big deal. I mean, it's certainly not ready to go and stick into your Tesla, that's true. So there's a lot of development work to go yet. And that particular market, which is halfway between the small-scale stuff for powering your cell phone or some wireless sensor device, and on the other end of the scale, sticking things behind solar panels, we haven't really addressed. Officially, we're supposed to be doing the small-scale stuff, and we're excited about the big-scale stuff, but we haven't got into the middle-scale stuff.
very much.